Greetings of the day. So today we are going to discuss in the module 1 stress and strain. In that we are going to discuss a few problems on bars with continuously varying cross section. Bars with a continuously varying cross section. So when the cross section varies continuously, an elemental length of the bar should be considered, and general expression we have to derive based on the given section. So here the bars may be made by using a circular section, or it may be in the form of the rectangular section. So there are two varieties of the bars with a varying cross section. One will be with a rectangular bar, So this is a rectangular bar. It is going to vary uniformly from the one end to the another end. So we'll consider here the breadth B1 and here breadth B2 and length. So length will be a L, and it will be a subjected to the load P. Subjected to the load P. So for the rectangular bar, so the derivation or to find out anyway the general or the normal expression for the regular bar will take the deformation dl will be is equal to PL divided by AE, but here it is a varying cross section. So varying a cross section, that is uniformly varying. So here B1 to B2, it is gradually the whatever breadth or width is going to be a decreasing gradually from the bigger end to the smaller end. So uniformly varying a cross section. So the total deformation for the rectangular bar with a varying cross section or uniformly varying cross section, the deformation will be is equal to P into L is common, P is the load and L is the length, divided by T is indicating thickness and E is Young's modulus into a B1 minus B2. So B1 minus B2. So here B1 will be at the bigger end and B2 will be at the smaller end. So the width is varying from B1 to B2. So bigger end is B1 and the smaller end is B2 into logarithm into log of B1 divided by B2. This is the expression we are going to consider to find out the deformation of the bar when the given cross section is varying from the bigger end to the smaller end when the load is applied, a tensile load. And there will be a one more section, the cross section may be a circular. If the given section is a circular cross section, so once again it is varying from the bigger end to the smaller end. So here we are going to consider the diameter. So bigger end will take the diameter D1, and at the smaller end we'll consider the diameter D2, and once again it will be subjected to the tensile load of P, and the bar is varying a cross section for the length of L, for the varying the length L. So for this the expression or the total deformation for the circular cross section we will take the equation dl will be is equal to 4p L 4PL divided by pi into E into D1 into D2, where P is the load and L is the length, and where E is the Young's modulus, and D1 will be the bigger end diameter and D2 is the smaller end diameter. So based on these two sections, we are going to solve the problem. So the problem is given like this. The given problem is a steel flat of a thickness 10 millimeter tapers uniformly from 60 millimeter at one end to 40 millimeter at another end in a length of 600 millimeter. If the bar is subjected to a load of 60 kilonewton, determine the extension. Take Young's modulus, or E is equal to 2 into 10 power 5 Newton per square millimeter. And what is the percentage of error if average area is used for calculating the extension? Here given is a steel flat thickness. Thickness is given, so here we can take, this is a given is a rectangular cross section. It is varying from bigger end to a smaller end, varying up from bigger end to a smaller end, and its thickness is given. So the thickness is 10 millimeter. Thickness is 10 millimeter. Tapers uniformly from 60 millimeter. Tapers uniformly from a 60 millimeter at one end to the 40 millimeter at another end, and its length is 600 millimeter. If the bar is subjected to a load, the bar is subjected to a load of 60 kilo Newton. Bar is subjected to a load of 60 kilo Newton. Determine the extension. Here it is asked to determine the extension and take Young's modulus. E is 2 into 10 power 5 Newton per square millimeter. And what is the percentage of error? So we'll note down the given information or given data. Thickness is given, T is equal to 10 millimeter, and it tapers uniformly from 60 millimeter at one end to a 40 millimeter at another end. So bigger end B1 will be is equal to 60 millimeter, and the smaller end or another end is 40 millimeter. So here the one end width is 60 millimeter. It is tapering gradually for the length of 600 millimeter, where up to reaching the width of 40 millimeter. And here the load is given. If the bar is subjected to a load of 60 kilo Newton, and here it is asked to determine the what is the extension. What is the extension of the bar? And Young's modulus is given. Young's modulus is 2 into 10 power 5 Newton per square millimeter. And also here it is asked to compute or calculate what is the percentage of error. What is the percentage error if the average area is considered? If the average area is considered, instead of using the whatever standard equation for the tapering cross section, if you are considering the average area by taking one end is 60 millimeter and another end is 40 millimeter, if you consider the mean area of the cross section of this uniformly varying a tapered bar, so what will be the error in the extension or deformation? Here it is asked to compute. So anyway, we know the extension of the tapering bar of rectangular section. We have the equation. So we need to take the equation of extension of the tapering bar of rectangular. Anyway, here the thickness is given, so we can take a rectangular cross section. So for the rectangular section, so dl, so anyway we have the derived equation. Dl will be is equal to P into L divided by T into E into B1 minus B2 into log of B1 by B2, log of B1 by B2. So here P is the load and L is the length and T is the thickness and E is the Young's modulus. B1 minus B2. B1 is the width at the bigger end and B2 is the smaller end width, and log of, once again, B1 is the width at the bigger section and B2 will be the width at the smaller section. So we can compute the total extension by considering the uniformly varying a tapered bar equation PL divided by T into E B1 minus B2 into log of B1 by B2. So load is 60 kilonewton and Young's modulus is 2 into 10 power 5 and 60 and 40. So width is 60 and 40. So load is 60 kilonewton is given. So 60 into 10 power 3, 60 into 10 power 3, and length is 600 millimeter is given, and the thickness of the section is 10 millimeter, and Young's modulus is 2 into 10 power 5 Newton per square millimeter, and the width is 60 and 40. So the bigger end is 60 and minus 40 is the width at the smaller end into log of 60 by 40. So if you simplify this, you will get the deformation dl will be is equal to 0.3649 millimeter. Anyway, it's a very simple. You just substitute directly to the calculator so that you will get the extension or the deformation is 0.3649 millimeter. So this is what they determine its extension. So the extension we got is 0.3649, and another condition is given is what is the percentage error if average area is used for calculating the extension. Instead of taking the actual area, if you are taking the average area, so what will be the percentage of error we are getting, that we need to find out. So here the given is if the average area or average area of cross section is considered, if the average area of cross section is consider instead of tapering or uniformly tapering cross section, what will be the extension? Anyway, we know the basic equation dl will be is equal to p into l divided by a into e. So here the area we calculated we got in terms of the t into b1 minus b2 log of b1 by b2. But here we are taking the average area. So the average area will be is equal to the average area. I'll take AVG. Average area will be is equal to 60 at the one end and its thickness is 10 plus the area at the smaller end is 40 and its thickness is 10. So for a area of the rectangular section, we know the breadth and thickness or width into thickness you can take. So 60 plus 10 plus 40. We need to multiply 60. Here we are finding the area of the cross section. So 60 into 10 60 into 10 plus 40 into 10 divided by mean means we need to take by 2. So here you'll get 60 into 10, you'll get 600 plus 40 into 10 is 400 divided by 2. So 1000 divided by 2 you'll get 500. So the area of cross section unit is millimeter square. So 500 square millimeter. So we know the basic equation for the regular bar extension dl will be is equal to pl divided by a into e. So here we are considering the average area. So pl divided by area average or mean area into Young's modulus. So p is equal to same, p is 60 kilonewton. So 60 into 10 power 3, and length is length was given is 600 millimeter, and the average area we computed or calculated value is 500 square millimeter, and Young's modulus is 2 into 10 power 5 Newton per square millimeter. So we'll get uh, the deformation after considering the average area will be equal to 0.36 millimeters. So when we consider the actual area, or by considering the tapered intersection, the deformation is 0.3649. If you are not considered the whatever the actual or the tapered cross section, instead we are considering the average cross section. Average cross section we are considering instead of the tapering area, we are getting the extension is 0.36 millimeter. So now here it is asked to compute what is the percentage error. What is the percentage error? So here also you can see the actual is 0.3649, but if you are considering the mean, it is we are getting a less deformation in comparing to the actual area of cross section. So the percentage of error will be is equal to 0.36 0.3649 0.3649 minus 0.36 over 0.3649, and in terms of the percentage we need to multiply with the 100, so the percentage of error will get 1.3428. So this is the percentage of error we are getting instead of taking the actual area, if you are taking the mean or the average area of the cross section. So let me recall from the beginning. Here given is a steel flat. Here a steel flat means it is a rectangular section. Thickness is 10 millimeter is given, and it is tapers uniformly from 60 millimeter at one end to a 40 millimeter at another end in a length of 600 millimeter. So we can construct the diagram like this. So one end is 60 millimeter and at another end is 40 millimeter, and its thickness is 10 millimeter and length is 600 millimeter. And if the bar is subjected to a load of 60 kilonewton, and what is the deformation? So whenever the tapering or the uniformly varying cross section is given, so we should not consider the basic equation of computing the deformation of extension PL divided by AE. Whenever the the area or uniformly varying section is given, means we should not consider this particular equation, uniformly varying cross section. We should not consider this particular equation. This is for the regular bar or the step-out bar. You can take DL will be equal to PL divided by AA. But here the whatever the flat or the rectangular section is varying from 60 millimeter to 40 millimeter uniformly. So we need to consider the standard or whatever the derived equation. We already derived the equation for the tapered cross section of the rectangular bar. So that particular equation we have to make use to compute the extension. And here given is take Young's modulus is 2 into 10 power 5. And later here it is asked what is the percentage of error if average area is used for calculating. Instead of considering the actual area, if you are considering the average area by considering one end is 60 millimeter and another end is 40 millimeter, we'll go with the average. So 60 into 10 plus 40 into 10 divided by 2. So what will be the difference or what will be the percentage of error we need to calculate? So here given is a extension of the tapering bar of a rectangular section. In the question it is given is flat, don't get confused. Whenever the thickness is given, means it is a rectangular section. So here DL will be is equal to PL divided by T into E B1 minus B2 into log of B1 by B2. P is the load. Load is given 60 kilonewton, so 60 into 10 power 3. Length is given, length is 600 millimeter, and thickness is known 10 millimeter, and Young's modulus is given 2 into 10 power 5 Newton per square millimeter. Here length and thickness is in millimeter, so we need to keep Young's modulus also in terms of Newton per square millimeter. And here B1 is bigger and width is 60 and smaller and width is 40. into log of 60 by 40. So we'll get the deformation is 0.3649. And next half of the question is, if average cross section or mean area is considered instead of tapering cross section, what will be the deformation and what will be the percentage of error? So for that, we are taking the equation dl is equal to pl divided by ae. So anyway, average area you can take 60 into 10 plus 40 into 10 divided by 2. So the average area we got 500 square millimeter. So we are, for the average area or for the regular sections, we have the extension of to compute the extension or the deformation, we have the equation is equal to pl divided by A into P into L. Here we are considering the average area. We are considering the average area into Young's modulus. So load is known, length is known, area is 500, and Young's modulus is known. So we'll get the deformation when we considered the average area of cross section instead of tapered area. The deformation is 0.36. So the percentage of error we can compute. So the percentage of error is 1.3428. So we'll move on to the one more question. So the next question is, given question is like this: a 1.5 meter long sorry a 1.5 meter long steel bar is having uniform diameter of 40 millimeter for a length of 1 meter and in the next zero point 0.5 meter its diameter gradually reduces from 40 to a 20 millimeter. Determine the elongation of this bar when subjected to an axial tensile load of 160 kilonewton, and take Young's modulus is equal to 2 into 10 power 5 Newton per square millimeter. So here in the first step is we need to confirm whether the given section is a rectangular or a circular. So here given is on a diameter, so you can straight away say that given is on a circular cross section. So we'll read slowly: a 1.5 meter long, so length is 1.5 meter long steel bar is having a uniform diameter of 40 millimeter for a length of 1 meter. For a length of 1 meter, so the total length is 1.5 millimeter, but for a length of 1 meter or 1000 millimeter, up to a 1000 millimeter or 1 meter, its diameter, uniform diameter is same or uniform. So diameter phi will be is equal to 40 millimeter and in the next zero point 0.5 meter anyway total length is 1.5 meter and in the next 0.5 meter, or else I can take 500 millimeter. So the total length is 1.5 meter. So 1 meter plus 0.5 meter out of 1.5 meter. So uniform diameter of 40 millimeter for a length of 1